right, so let's talk about one of the most interesting and most important to our lives type of waves, which is light waves. And it turns out that light waves are really part of a bigger category of electromagnetic waves. The light that we can see is electromagnetic waves of a particular range of frequencies or a particular range of wavelengths. If you have an electromagnetic wave and it has a frequency between about 3 and 8 times 10 to the 14 hertz, you will be able to see that as light. If the frequency falls outside that range, then you won't be able to see that electromagnetic wave, but it still has basically the same set of physics that light waves do. So sometimes we use light waves to describe specifically visible light that we can see, but also sometimes people will say the phrase light waves, and what they really mean is more the broader electromagnetic waves, which is called the electromagnetic spectrum. The speed of light is really the speed of all electromagnetic waves, and it is abbreviated with the lowercase c, and it has a value of 3 times 10 to the 8th meters per second. This is really, really fast. In fact, it's the fastest that anything ever can go. So here's a question. What is a light wave? What is it sort of made of? We know that waves are basically ripples or disturbances in something that move. So it would be fair to ask, what is being disturbed? What is changing when a light wave moves through a region? Right? If I take a slinky and I move it like this, and I ask you what's changing is the height of the slinky from its normal resting position. With a light wave, the thing that is changing in a particular location in space is the electric field and the magnetic field. I could label each point along this slinky and ask, as the wave moves, what is this location's height from its normal position? What is this location's height from its normal position? We can also ask, what is the electric field at a certain point in space? And how is it changing? And you might remember that a changing electric field makes a magnetic field, and also a changing magnetic field makes an electric field. And both of these that are made are perpendicular to both the velocity in question and the other field. So here's what this picture is showing. The wave here is moving in this direction. We have an electric field moving vertically on the page, up and down. And as that changing electric field moves, it creates a magnetic field that is perpendicular to it. So this is supposed to be basically like the electric field like this, and the magnetic field like this, going through it in the opposite direction. So this magnetic field is coming out of the page, into the page, out of the page, into the page, whereas the electric field is moving up and down. This is a more detailed picture than you'll ever have to be tested on, but I think it's a really cool looking picture, and it kind of helps you draw the connection between why these are called electromagnetic waves, because they really do have both an electric and a magnetic field. And what's going on is that the changing electric field is causing a magnetic field. The magnetic field changes and causes the electric field. So these fields kind of pull and push on each other in a way that allows the wave to move like a wave, like a ripple through space. Okay. So we know that the speed is always 3 times 10 to the 8th meters per second for any electromagnetic wave. If we get a fast enough frequency of a certain range, we will see that as a light wave. And on the reference table on page 2, there is the electromagnetic spectrum. Which lists out all the different types of electromagnetic waves based on both their wavelength and their frequency. If we know one of those two things, we know the other one, because we know that the speed should equal the frequency times the wavelength. And in this case, the speed is 3 times 10 to the 8th meters per second. The frequency in this problem is unknown, and the wavelength that we're given is 612 nanometers. So to be able to use this in the equation, we'll need to convert. So we're given the wavelength. We know the speed because we know that it's light, so the speed is always this number. And we want to know what the color is. We will address this part in a second. But first, we know we can figure out the frequency. So the frequency, before we do that, we need to find the wavelength. So the wavelength is 612 nanometers. A nanometer is 10 to the minus 9 meters. So you could write this as 612 times 10 to the minus 9, or you could write 6.12 times 10 to the minus 7. If you multiply these two things, that's what you get in meters. So let's plug these two things in. 3 times 10 to the 8th meters per second equals our frequency times 6.12 times 10 to the negative 7th meters. Divide both sides by this. And you will see, for the units over here, meters are going to cancel and we just have per second left. We're finding the frequency. Remember that that per second unit is hertz. So I'm going to get the calculator out. I've got 3E8 divided by 6.12 E negative 7. Oops, I typed it in wrong. There we go. It's 4.9 times 10 to the 14th hertz. Okay, now I want to know what color this is. So for this, I'm going to need to use the reference table. On the reference table, I don't have a printed out one, it's on my computer, but there's this little chart that has the visible light. And the light is split up into kind of rainbow colors. And we're going to look for the color where this frequency is in the correct range. It has the frequencies listed out for each color. So we're going to try to figure out which color this frequency falls into. And what it says, I have yellow, orange, this isn't the whole thing, red, but between yellow and orange, it says 5.03 times 10 to the 14th. And between orange and red, it says 4.82 times 10 to the 14th. So, my answer of 4.9 times 10 to the 14th hertz falls into this range. So this must be orange light. If you create an electromagnetic wave with this frequency, which is a lot of waves per second, you'd have to be moving your electric field really, really fast, and you sort of sent that wave out into the world and somebody saw it, they would see an orange light. Cool. You could also do questions like this that are based on the broad categories of waves rather than specific colors, and those would just be a bigger frequency. For example, on the spectrum, we see that AM waves have a frequency of around 10 to the 6th hertz. So let's say if we have an AM radio wave with a frequency of, I don't know, 1.5 times 10 to the 6th hertz, we could find the wavelength of this wave. This is a lot slower of a frequency than light waves. Remember, what matters here is the exponent on the 10 and not really this number in front as much. So this is a much slower wave. So think about whether you think that it has a longer wavelength or a shorter wavelength. We could also just figure it out in the formula, which is what I'll do next. So for V, I know it's still 3 times 10 to the 8th meters per second. Even though this is a radio wave, it's still the speed of light. In the phrase the speed of light, when they say light, they really mean the broader electromagnetic spectrum. So 3 times 10 to the 8th equals the frequency times the wavelength. And then let's find the wavelength by dividing both sides by this number. 3E8 divided by 1.5 E6 is 200. So this wavelength would equal 200 meters. Radio waves are really big. Light moves very fast. So even though this frequency seems pretty fast, it's happening 1,000,000 times per second. The light moves so fast that each of those waves is 200 meters long. Cool. And if you got a question that said, what type of wave would a 200 meter long electromagnetic wave be? You could look at the chart, either based on the frequency or the wavelength, and see which of those sort of boxes it falls into. Okay. Let's talk about polarization. So this electromagnetic field stuff seems very weird, and it's worth asking, like, how do we know that this is really what's happening? How do we know that a light wave is really considered a transverse wave and not a longitudinal wave? How do we know that something is moving up and down? And one property that light waves have that's pretty interesting is polarization. You might have heard of polarized sunglasses, and if you have a couple pairs of polarized sunglasses, you can probably do a version of one of the sort of experiments I'm going to do on your own if you want to. But you'll kind of need two separate polarized things for this to work. But before we do that, let's talk about polarization on a big scale, enough that you can see. So this piece of an egg carton represents a polarizer. And what it means is that it's only going to let through some types of waves. Now, if I make a transverse wave on the slinky, it passes through this just fine. The wave goes through. But this is not the only way that I could make a transverse wave on the slinky. I could also make a transverse wave going this way. And if I wasn't inside the egg carton, this would work fine. But if I try to start a transverse wave that's going this direction, it can't make it through this slit because it's being blocked here. So a transverse wave has more than one possible direction. We know that the movement of the slinky is supposed to be perpendicular to the actual slinky itself, but there's two ways to be perpendicular to this slinky. I could move this way, that's perpendicular to the slinky, and this goes through the slit fine. Or I could move this way, this is perpendicular to the slinky, but it can't move through the slit that way. So it just kind of gets stuck there. So a polarizer will let certain transverse waves through if the disturbance is in the allowed direction, and it will block other waves that are in the not allowed direction. Longitudinal waves don't have this property. I can send a longitudinal pulse through here. There's no wrong direction to move here because there's really only one way to move parallel to the slinky. It's this way. But to move perpendicular, I could move in this way, which is allowed, or I could move in this way that's not allowed. So let's make some notes about polarization. So only transverse waves are only allowed through if the disturbance is in the quote-unquote right direction. Longitudinal waves can always get through. You could have a barrier that blocks all longitudinal waves, but it wouldn't be able to choose some longitudinal waves and not others because there's no way to choose between them. They're all moving in the same way. So they can always get through by the same amount. There's no sort of hidden separate factor in longitudinal waves, whereas in transverse waves, you could ask how much is it moving, how fast is it moving, what's the amplitude, but there's also this polarization, which is just the word for what direction is the disturbance in. Is it in this direction or is it in this direction if the slinky is going this way? And we cannot see by looking at it what the polarization of light waves are. If you shine a light full of up and down waves versus left and right light waves in somebody's eye, it will look the same to them. Our eyes can't detect that difference. So it might seem initially like maybe light waves are longitudinal waves because they seem to always get through by the same amount. But if we have something that acts like this egg carton, we can test for that. And the way we're going to do that is by combining two polarizers together. So you can see that this is letting some of the light through. This is like a piece of a movie 3D glasses that I got from a Harry Potter premiere, which is why it's round. Anyway, we can see that it's letting some of the light through, but not all of it. You can still read the words through this. But that doesn't necessarily tell us whether it's really polarizing, whether it's really choosing specific directions of light waves and not other ones. But I have a second one here, and we can line them up with each other. Right now, they're pretty much the same amount of dark. They're both letting through kind of the same amount of light waves. But if I turn one of these pieces, we can see that it gets way darker. So what's going on here is that when they are both oriented the same direction, then the light waves that are going this way can get through. The light waves that are going this way can't. Some of the light waves can get through. But if I have one of these blocking vertical light waves and one of them blocking the opposite direction light waves, suddenly no light waves can get through, because one of these is blocking one direction and the other one is blocking the other direction. So depending on how I turn these, they can either agree about which light waves to block and some of the light waves can get through, or they can disagree and this is blocking some of the light waves. This is blocking the other half because it's perpendicular to it. And so now none of the light waves can get through. It's a pretty weird effect. If you ever wear 3D glasses in the movies, go to the bathroom and look in the mirror, because if you close one eye and then the other, the effect is super weird. This is how they send two different images to your eyes in 3D movies, is they send one image that's polarized one way that can get through this side, and another image that's polarized the other way that can get through the other side. So then when you watch the movie, your two eyes are actually watching two different polarized movies. And if you take your 3D glasses off, you'll just see kind of the two images on top of each other. But when you wear the glasses, this one lets one image through, this one lets the other one through. It's a way to choose which light waves to let through, and they can either agree or they can disagree. Cool. The way that these things are made, the reason that sometimes a certain direction of electric field can get through and a certain one can't has to do with the actual molecules that make these up and the way that the electrons in those molecules can move. It's set up so that the electrons in those molecules can move in some directions and not in other directions. And that causes the polarizer to absorb some of the waves and let some of the other ones through. So light waves must be transverse because they can have different polarization. Meaning we have a way to choose which direction of light waves we want to allow through. Okay, hope that was interesting. A lot of it is connected to stuff that we've already learned about. It's not only light waves that can be polarized, but that's the application that you see the most. But obviously any type of transverse wave can be polarized, just like I was showing you on the Slinky. All right, hope that you had a good weekend. Let me know if you have any questions, and I will talk to you again soon.